Hi, I'm Jacob. I'm one of the students working on Aarhus University's submission to the 2023 IEEE SciVis contest. The contest features data from a neuronal network simulation that model activity in a brain just like this one. In this video, I present our solution for visualizing and exploring the contest dataset. We can already see behind me the first simulation starts with no synapses. Over time, it builds the initial neuronal network. What we can see is, well, that we can't really see much, since all the synapses, having formed, completely occlude the display. So, as a first step, we reduce complexity by clustering together highly connected neurons. Now, that's better, but there are still a lot of synapses cluttering the view. Let's untangle the visualization a bit more and draw those synapses going in the same direction as bundles instead of individual lines. That looks much better, and even from here, I can see some interesting patterns appearing. Let's take a closer look at it. Now we're standing in front of the simulated brain. Let's take a deeper dive into it. Here we see the synapses bundled together into these red and white lines. The thick red lines connecting the clusters signify that there's many synapses going between these clusters, whereas the thinner white lines signify that only a few synapses connect these. So let's step outside and take a closer look at this cluster. Using the zoom tool, we can expand the cluster to see how the synapses then go into the subclusters and how the subclusters also are connected in between. We can even dive further in, expanding the cluster even further, in the end revealing the individual neurons. Thanks to the hierarchical nature of the clustering, we have a number of different levels of detail at our disposal, so we can drill down to just the right level of complexity. On every level of detail, the brain network is more or less fully connected. But because we bundled and clustered the data, we can distinguish between strongly and weakly connected regions. Now, let's take a look at how this state of the simulation came about. We see here that the simulation starts out with no synapses in any of the clusters, and then synapses start forming over time in this oscillating manner. This continues until the formation process subsides and the neuronal network reaches a steady state without any big changes in the synaptic connectivity. In line with current understanding of brain activity, smaller changes are constantly happening, as can be seen from the curves continuing to fluctuate to a smaller degree. Towards the end of the simulation, we can observe this small dip right here. It is interesting that this obviously affects the whole brain, as the dip is visible for all the clusters. This may be due to the activity of inhibitory neural circuits, which can temporarily alter the overall dynamics of the neuronal network. Now, let's move on to something a bit more interesting, like how the simulations behave when perturbing this steady state that we reached after the initial buildup. Let's save this state for further analysis later. This is what the other simulation runs in the dataset are about. And first we look at the simulation in which active stimulus is applied to the neuronal network. We can see from the temporal view that there are two clusters that exhibit almost no immediate effect to the stimulus. Selecting them with our selection brush like this, and this reveals to us in the topological view over here in the brain that these two clusters are located in the front of the brain and actually are just adjacent to each other. We can also observe some of the other clusters that have more dramatic change, like this one and this one. Looking at the topological view again, we can see that these clusters are also placed adjacent to each other, but this time in the back side of the brain. We can then observe that regardless of the severity of the impact of that stimulus, all regions of the brain then fluctuate in their connectivity before reaching a steady state. Interestingly, the stimulus seems to have a lasting impact on the synaptic connectivity, with the recovered state actually being lower than the original one. Let's save this insight for later analysis. Now let's compare this to another simulation. For example, the one where certain areas of the brain are deactivated. This would be the case if one suffers a lesion of the brain, for example due to an accident. But how does the simulated brain react in this case? We can see the deactivated regions here as gaps in the network. When exploding the clusters around this area, we can drill down the neurons that were disabled in the simulation. Using the cluster zoom tool, we can expand this further out. And looking at this, we see this cluster here that is obviously not connected to anything else, which is why there are no synapses shown to it. We also see that the adjacent clusters actually have these really wide red edges, meaning that they are strongly connected just next to it. Let's take a look at the temporal view for this simulation run. We can clearly see that some of the clusters form fewer connected dendrites than others. Let's see where they are located in the brain. So for instance, we have this cluster right here and this cluster right here. The clusters that are selected with our brush are now colored red, and since the two views are linked, they are also highlighted in the brain visualization. We can see here that the highlighted cluster actually includes some of the disabled neurons. On the other side of the brain, we see the exact same pattern where the disabled area are part of this cluster, which shows the low connectivity. Finally, let's explore the effect of different perturbations on the brain structure by looking at the final state of all simulations side by side. So here we looked at the disabled simulation. Going back to what we have previously seen, we started out with the no network simulation. Then we went on to the stimulus simulation. So now we have these three simulations next to each other. Let's make them look a bit more like each other by using the format painter. So the idea with the format painter is that we want to apply the time step along with the rotation and scale and the explosions of one brain, apply that to the other views, so it makes it easier to visually compare them. So now that we have format painted the three brains to have the same setting, we can easily do side-by-side comparison of them. Over here we have the disabled simulation with the neurons that were turned off. In the bottom here, we had our initial simulation using the no network simulation. And on top here, we have the stimulus simulation. Taking a closer look at these, we can inspect how the slight differences in the synaptic connections in the individual brains really come out. So let's show this to someone. Hey Marius, look at the insight I found in the disabled simulation. So this has been our submission for the competition this year. We have seen how we can use our application to solve all 4 tasks set out by the competition. We first got an overview of the data. We then analyzed the plasticity changes of the brain. We looked at the simulation runs in an ensemble, all put together in one application that enables this flexible workflow. Thank you for watching, and see you at the VIS conference.